Hello everyone. In this video, we are going to work through a specific problem which covers two pillars of computational fluid dynamics, the method of characteristics for hyperbolic problems and the finite volume method for diffusion equations. We will start with the method of characteristics, a beautiful mathematical technique that gives us the exact solutions to certain nonlinear wave problems. We will apply it to a classic piston-driven compression wave and then move on to drive the finite volume discretization for the steady diffusion. I will be focusing on the concepts, the reasoning, and the physical meaning, while the equations will be displayed on screen side by side. So let us begin. Before diving into the piston problem, let us understand the method of the characteristics itself. In fluid dynamics, many flows are governed by hyperbolic partial differential equations. These equations describe how disturbances propagate at finite speeds. Think of the speed sound waves, shock waves, or water waves. The key property is that the information travels along specific curves in space-time called characteristics. The method of characteristics exploits this. We find these characteristic curves and then transform the original partial differential equations into the ordinary differential equations along them. So these ODEs are often much easier to solve. Why is this important? Because it gives us a way to understand wave interactions, determine how many boundary conditions are needed, and even construct exact solutions for problems like the one we will solve today. So in modern CFD, characteristics are the foundation of Goodenough type schemes and Riemann solvers, which are used in virtually all compressible flow codes. So by understanding the method, you gain insight into how these numerical methods work. So when is it used for solving the inviscid compressible flow problems analytically, for example, the shock tubes and expansion fans, for designing the numerical boundary conditions, the characteristic boundary conditions, or for analyzing the stability and the wave propagation in the numerical schemes. So let us apply it to our piston problem. We have a semi-infinite tube filled with a perfect gas. Initially, the gas is at rest, velocity 0, and the uniform pressure P naught, density rho naught, and the temperature is T naught. So at T is equal to 0, a piston at the left end starts moving to the right with the velocity with the constant velocity up. So we assume the piston speed is small enough that the flow remains isentropic, no shocks, and the entropy is constant. So the gas is ideal. So P equals to C times rho raised to the power gamma, where gamma is the 1.44 air. The flow is governed by the one-dimensional Euler equations for isentropic flow. These are non-linear, but they can be rewritten in the characteristic form. Now, the equations are the continuity and the momentum equations as displayed. So, using the isentropic relationships, we can express the pressure gradients in terms of the density or the sound speed. The speed of the sound is represented as A is equal to gamma P over rho whole under root. So through a combination of these equations, we can derive the Riemann invariants as displayed over here as J plus and J minus. So it turns out that the J plus equation is constant along the curves where d of x over d of t equals to u plus a, while J minus is constant along dx over dt equals to u minus a. So these curves are called as the characteristics. The first family, which is J plus right running, carries the disturbances to the right, while the second J minus left running carries them to the left. Now, this transformation is the heart of the method. Instead of solving the original PDEs, we track how these invariants propagate. Now, let us think very physically that the characteristic speeds are u plus minus a. So, for a gas at rest, these are plus minus a naught. For small disturbances travel at a speed of sound in moving gas situation, they are carried along by the flow. So the Riemann invariants tell us that the certain combinations of the velocity and the sound speed are remembered along these paths. For our problem, ahead of the wave, the gas is undisturbed, that is u is equal to 0, and for this a would be equal to a naught. The left running characteristics come from a region, from this region, so therefore J minus is constant everywhere and equals its initial value. So J minus would be equal to minus 2 times A naught divided by gamma minus 1, and so this would be giving us an algebraic relation between U and A anywhere in the flow, and we can represent U as displayed over here, U equals to 2 over gamma minus 1 A minus A naught. So if we know the U value, we know A and vice versa. Now the piston generates a compression wave since the only disturbance originates at the piston. Only the right running characteristics carry the information. So this is a simple way. One family of characteristics is the straight lines. Uh, Consider the characteristic that leaves the piston at some point. At the piston face, the gas must move with the piston velocity u equals to up. Using our relationship, we can get A equals to A naught plus gamma minus 1 over 2 times UP. But both U and A over here are constant along that characteristic. Therefore, the slope of the characteristic is also constant. So, the characteristic is a straight line, and all such characteristics from the piston have the same slope. They are all parallel. Consequently, the entire region between the piston and the wavefront has uniform properties. That is, U equals to UP, and A would be equal to A naught plus gamma minus 1 over 2 times UP, and the constant pressure and density. So the wavefront is the leading characteristic that started at t is equal to 0 initially from x equal to 0 and travels at A naught, since ahead of it the gas is undisturbed. Its position is now x equal to a naught times t. So for thus the solution would be for x values of greater than equal to 0 and less than equal to a naught times t. We would be saying that u equals to up, and a would be equal to a naught plus gamma minus 1 over 2 times up. But what happens when the x values would be greater than a naught times t? We would seeing that the u would be equal to 0 and a would be equal to a naught. Now, what does this mean physically? The piston compresses the gas immediately in front of it, creating a uniform slug of the high pressure gas that expands at the constant speed. And now the wavefront moves at the speed of sound while the piston moves slower. Using the isentropic relationship, we can compute the pressure rise as P over P naught relationship over here. So for UP over A naught, this approximates that P is approximately equal to P naught plus rho naught A naught times UP, which is the actually the representation of the acoustic linear result. But our solution is exact for any UP as as long as the flow remains isentropic, which means that there is no shock. So this example illustrates the power of characteristics. We solved a nonlinear problem analytically by tracking the information propagation. Now that we have seen how characteristics give insight into the wave physics, let us shift gears to a different but equally fundamental topic, the finite volume method for the diffusion. This method is the backbone for most CFD solvers. Now consider this steady diffusion equation as displayed over here, in which phi is a scalar like temperature, and the coefficient, the diffusion coefficient, which I would be pronouncing as the half t, and s is here the source term. The finite volume method is based on the integral equation, as we all know that, and instead of discretizing the differential equation directly, we divide the domain into control volumes and enforce the conservation of phi over each volume. So this ensures that the numerical solution respects physical conservation laws. Now, take a control volume around the node P and extending from the face W to face E. Integrate the equation. We can get the integral equation as we can see over here. The first term is the difference of the fluxes at the faces. So this is the net flux into the control volume. The second term is actually the total source within the volume. So the equation says as the net flux plus source equals to zero, which is exactly the conservation. Now to evaluate the fluxes, we need to approximate the gradient at the faces as well. The simplest choice is to assume a linear profile of phi between the nodes. Then we can write the equation as d phi over d of x at point E would be approximately equal to phi E minus phi pi divided by phi p divided by delta of x. And likewise, we can write the equation at the w. So here delta x is the grid spacing, which is actually the uniform grid spacing, and the diffusion coefficients at point E and point W are evaluated at the faces, often by harmonic averaging of for the variable properties. So the source term is approximated by the midpoint rule. So we can write the integral of s with respect to d of x is approximately equal to sp times delta of x. So for generality, we linearize the source term as s equals to sc plus sp times phi p. So this helps when solving the system iteratively. Now, moving on to the algebraic equations and coefficients, we substitute these approximations into integrated equation, which gives us this particular equation, and multiplying this equation then by delta of x and collecting the terms and rearranging it to the standard finite volume form, where we can get the final form as AW equals to the diffusion coefficient at point W, and likewise at the different points as well. So the source term would be equal to SU equals to SC times delta X whole square. Now, moving on to and understanding the interpretation and the significance of this concept. So this equation tells us that the phi p is a weighted average of its neighbors plus a source contribution. The coefficients AW and AE represents the diffusion conductance between the nodes. So why is this method so important? It's because it is conservative by construction. Fluxes are balanced exactly. Secondly, it works on the unstructured grids and complex geometries as well. Thirdly, the coefficients have a clear physical meaning, which helps in developing the bounded and stable schemes. So the derivation we did is the simplest form, but the same principles extend to unsteady problems, convection, and multi-dimensions. So today we covered two fundamental topics, the method of characteristics and the finite volume method. In the method of characteristics, we saw that it gave us an exact solution for a nonlinear wave problem, showing how information propagates along the characteristic curves and how Riemann invariants simplify the analysis. Secondly, in the finite volume method, which we have just studied, provided a systematic way to discretize diffusion equations while preserving conservation. So both these concepts are essential for anyone working in the CFD. I hope this explanation helps you with your problem and deepens your understanding. If you have any questions, please leave them in the comments, and thank you for watching.